This video is an overview of Euler's method. We want to understand the concept of Euler's method and how it's used to approximate solutions to differential equations. Now, before we go any further, let's just focus on this name here. This looks like Euler, but it's pronounced Euler. Euler was a Swiss mathematician living in the 1700s, an absolutely brilliant mathematician who just did tons and tons of research on mathematics, wrote tons of papers, solved lots and lots of really cool problems. Math would not be anywhere near where it is today if it weren't for this mathematician Leonhard Euler. So we pronounce the name Euler, not Euler as it looks. So we want to understand this method that's named after Euler. And let's talk first about the background. Let's imagine that we have a differential equation of the form y prime equals a function of x and y. So we have a first order differential equation. This is the same form that we saw for slope fields. And we want to really think in the context of slope fields here. We also have an initial condition. We're told that the solution at the x value x0 has a y value of y0. So when we have a differential equation along with an initial condition, this is called an initial value problem, IVP, as we've seen before. And when we see this expression y of x0 equals y0, this initial condition means that the point x0, y0 is on the graph of the particular solution that we're trying to find. Euler's method is a technique for finding points that are approximately on the curve of the particular solution. So let's talk about the philosophy of how Euler's method works, and then we'll see a graphical example. So imagine sort of an odd situation here. Imagine that you're in the woods and you're blindfolded and you're trying to follow a trail that goes through the woods. And you have a friend who is guiding you along the trail. They're telling you the direction to go as you progress along the trail. So you start at some point in the trail and you can take a step straight in any direction. So your friend points you to go a step straight in a certain direction and you're roughly going to be following the trail. Then after one step you stop and your friend sort of redirects you, tells you to go a step in a slightly different direction to try to stay on the trail. And then you take a step again after being redirected. You take another step to go along the trail. Then your friend redirects you a bit more. You take another step. And we have this kind of piecewise trying to follow a trail like this. This is really a good picture of what Euler's method does. We are going to work in the context of a slope field, and we can think of the arrows of the slope field as being the friend who's guiding the movement along the trail. So let's imagine starting at some starting point x0, y0, and we'll draw in some axes here and try to think of the context of a slope field. So we have a slope field here. Let's just say it's y prime equals some function of x and y. We're not going to try to draw a representative slope field here, but just imagine that there are lines here that are directing particular solutions for whatever our differential equation is. So we're going to start at a certain point, x0, y0. Let's say that that point is right here. So here's the point with the x value of x0, y value of y0. There's the point x0, y0. And we are going to move a short distance in the direction of the slope field. And it's going to be a short distance straight in that direction, just perfectly straight. So maybe the slope field here, we have some small line segment that tells us the slope. So we're going to move straight in the direction that the slope field tells us to go. And we'll arrive at some new point. Let's call it x1, y1. So we get to this new point, x1, y1. This point will almost lie on the solution curve. So the solution curve might look something like this, and the point will be pretty close to being on the solution curve. Or maybe the solution curve looks something like this. We don't really know. But this point will be approximately on the solution curve. And we continue this process. We reset this new point to be the starting point, and we continue to find more points. Now, let's try to figure out what the coordinates of this point are. We're calling the point x1, y1, but what's x1 and what's y1? So we're going to start at this x value x0, and we'll take a small value that we call h, which is called the step size. H is the distance that we go in the x direction. So we're going to go a distance here of h, straight along the x direction. And if we go a distance of h from x0, this is the new x value x1. So the way to get x1 would be to take the old x value and add the horizontal distance h. So there is the x value of this new point. We move h horizontally. So starting at x0, we add this distance h, and we get to the new x value. So x1 is x0 plus h. How do we find the y value of this new point? We're calling it y1, and how do we get it? Well, let's think of what's happening here at our starting point. Here we have this small line segment, and the slope here is dictated by the differential equation. So let's talk about the slope here of this small line segment. The slope here, I'm going to think of it in a couple different ways. I'm going to first call it rise over run. We can think of a slope as a rise over run. And the rise is the change in the y values. So this is the rise. The run is the change in the x values. So here's the run, and we can think of slope as rise over run. Now, the rise is what we're going to add to the old y value to get to the new value. What is the run? Well, the run is just this horizontal distance h. So we can call this, instead of rise over run, let's just call it rise over h. That's the run here. So here's one way to think about the slope. But another way to think about the slope is that the slope is the value of the differential equation at that point. So we have the point x0, y0, and the slope at that point, sure, it's rise over run, but more precisely, the slope is the value of the differential equation at that point. So the slope can also be written as f of x0, y0. Now, using this expression, we can solve for the value of the rise here. So we get rise equals h times f of x0, y0. In other words, the distance that we have to add to y0 is this expression right here, and that will get us to the new point y1. So the new point y1 is the old y value, y0, plus this rise, which is h times f of x0, y0. So that's the way to get to this new y value for the new point that we get moving in the direction of the slope field. So the new y value is the old y value plus the step size times the differential equation evaluated at that initial point. Now, how do we get the rest of the points if we're going to continue this process? We're going to start now at the new point, and we basically reset everything. We just repeat this procedure to find more points. So based off of this, we can write down an algorithm for Euler's method. And an algorithm here is just a step-by-step process for solving some problem. In this case, the algorithm gives us the points that we get from Euler's method. So approximate values for the solution of this initial value problem with some step size h. We take different x values, and the way to get the new x value is just to add the step size to the previous x value. And the new y value is the old y value plus the step size times the differential equation at the old point. Now notice the similarity between this equation here and what we just developed. Really, they're saying pretty much the same thing. This equation here is saying that the way to get the new y value is to take the old y value and add the rise here, which is the step size times the slope at the previous point. So this gives us all the new y values for the points, and we can continue this process as long as we like. Eventually, as we continue to get more points, they'll start to stray further and further from the actual solution curve. So this is not an exact method for finding the solution, it's just an approximation. And the way to get a better approximation is to use a smaller step size. So the smaller the step size, the closer the approximation will be. The disadvantage with using a small step size is that we can't get very far very fast. We have to do more steps if we're just moving small increments here. So if we use a large step size, we can get further along the curve, but it's less accurate. If we use smaller step sizes, we can't go as far along the curve, but it will be more accurate. This process is inherently numerical. This requires a bunch of calculations, and really this is best done by a computer. So in the lab component of the course, you will see how to code this algorithm in Mathematica and find different approximations using Mathematica. For our purposes, we just want to understand what Euler's method does graphically. So let's take a look at this example. Here we have a slope field given below. It's the slope field that corresponds to the differential equation y prime equals 1/2 x. So there's the slope field for that differential equation. We want to plot, just graphically, the first 5 iterations of Euler's method, and we're going to use step size h equals 1. This will allow us to approximate the solution for this initial value problem. We have this differential equation, and this is the form that we need. We need y prime equals some function of x and y This is in the proper form, and here is our initial condition. And once again, this initial condition means that we have a point that the solution curve passes through. And this point, this is the x0, y0. This is the starting point for Euler's method. So the x value is 0, the y value is -4. That's the point where we're going to start Euler's method. Now don't worry, we don't have to use all of these expressions here. You'll do this later with Mathematica. We just want to understand in the picture, in terms of the slope field, what's going on with Euler's method. So we want to know, after 5 iterations, what does the approximation give us for the y value when x equals 4? So let's go to the slope field here, and let's work through Euler's method graphically. We're going to start at the point 0, -4. That is this point right down here. And we're using a step size h equals 1. So our initial point is x0, y0 equals 0, -4. Now Euler's method says, look at the point where we start and follow the direction of the slope field horizontally, a distance of h, so we're going to move a distance of 1. And if we look at the scale here, 1 is halfway in between, here's 0, here's 2, here's 0. So 1 is going to be right here. So we move a horizontal distance of 1 following exactly the direction that the slope field gives us. We have a horizontal line here, so we're going to move perfectly straight across. So we move a distance h of 1 horizontally. That right there gets us to the new point. Here's the point x1, y1. Now we stop and we reevaluate. We look at the direction given by the slope field. Now the direction is pointing us this way. So we move parallel with that line, exactly in the direction of the slope field, and that will get us to a new point somewhere over about here. So we move precisely in the direction of the slope field, following this new slope. This gets us the new point, x2, y2. Now we do the same thing, we just repeat the process. Move in the direction of the slope field, so now I have a bit steeper of a slope. We're still just moving a horizontal distance of 1. But we move parallel to these lines, so something like that. That's going to be the new x value. So we get to this x value here. That would be x3, y3. Now once again, we reevaluate the direction of the slope field, going a little bit steeper now. And we get to this point right here. Once again, we move a horizontal distance of 1 across. So we have 1, 2, 3, 4, 5 iterations of Euler's method, and we reach this point. Now, we were supposed to find what does the approximation give us for y of 4. So what we've graphed here, this is an approximation to the solution curve. The solution curve might look something more like this. We don't really know. We just have approximate values that are close to being on the solution curve. So y of 4, that is the y value that we found when x equals 4. And y of 4, it looks like it's at, I don't know, roughly -0.3 or something. So we'll just say our approximate value for y of 4 is approximately -0.3. We're just using approximations here. So that would be the approximate value that we get for the y value of the solution curve when x equals 4. Now let's look at the last part of this problem. What is the true value of y of 4? How do we find the exact value here? Well, to find the exact value, we need to solve the differential equation. So to find the true value, we must solve this differential equation. We have not seen a technique in general for solving a differential equation. We're going to learn one later on, and we talked about how there are many different techniques for many different types of differential equations. In general, it's really difficult to just solve a differential equation. So can we solve this differential equation? Well, in this case, yes, we can, because y prime is just a function of x. How can we find the function y? We can simply integrate. Now, most of the time, this will not work. We can't just do a plain old integral to solve a differential equation. This is just a very special case where y prime just so happens to be in terms only of x, so we can find y by using a simple integral. So in this case, y is the integral of 1 over 2 times x, integrating with respect to x, and the antiderivative of x is x squared divided by 2. So we have 1/2 times x squared divided by 2. That's x squared divided by 4 plus c. So this is the general solution. Y equals x squared divided by 4 plus c. That's the general solution. But we want to find the specific solution or the particular solution that satisfies this initial condition. So using x equals 0 and y equals -4, we will be able to solve for that value of c. So if we plug in x equals 0 and y equals -4, then we will get -4 equals 0 squared over 4 plus c. Well, 0 squared is just 0. So we just have 0 plus c. So c equals -4. So we have the particular solution here, and this is the solution for our initial value problem. Y equals x squared divided by 4 minus 4. So now that we have the particular solution, the precise solution to this initial value problem, we can find the exact value of y of 4. We can just find this by plugging in 4 into this solution. So y of 4 equals 4 squared over 4 minus 4. Well, 4 squared is 16 over 4, that's 4, and 4 minus 4 is just 0. So the exact value of y of 4 is 0. Notice how that compares to our approximation. The exact value for y of 4 is right here. Our approximation is actually pretty close. We're just about 0.3 away. So really, Euler's method was pretty effective here in finding an approximate solution to this differential equation. If we were to plot the solution curve, we would have a parabola opening upward, shifted down -4. It would look something like this. That's just kind of a rough sketch, but we can see how the different points that Euler's method gives us are pretty close to being on that solution curve. So once again, Euler's method is a numerical method for determining approximate solutions to a first-order differential equation with an initial condition. We're just seeing graphically how Euler's method works here, and in the lab, you'll see how to find the exact values of these points using Mathematica. Euler. This is a Swiss
method. Euler was a Swiss mathematician.
Euler.